So I guess to kick off our very first Chalk Talk for the month of March, this is Raul Marquez Montes, and he's going to be giving a presentation on understanding the electrochemical double layer capacitance measurements to estimate electrochemical surface area. And his abstract is estimating the ECSA is critical to report intrinsic properties of electrocatalysts. Measuring the double layer capacitance offers a versatile and non-destructive alternative for estimating ECSA when other techniques are unavailable. However, ion transfer reactions and improper experimental conditions can result in inaccurate capacitance double layer values and thus erroneous estimations of ECSA. So in this Chalk Talk, Raul is going to describe how the electrochemical double layer capacitance is determined using cyclic voltammetry, and then explain why the experimental conditions are critical to providing reasonable and accurate estimates. So yeah, anyways, I guess you can kick it off and we'll sit down. Yeah. Oh, and also there's refreshments in the room off to the side. For those on Zoom, that's what you're missing out on. And yeah.
Yeah, cool. And make sure to join our chapter, follow us on Twitter, Facebook. We have a website now, and we also have a listserv. We didn't bring the sign-in sheet, but if you want to contact us, any of us, our emails we sent out an email to all the students in mechanical materials and chemical engineering. I don't know if we hit chemistry, so but get into contact with us. We're gonna have a lot more meetings and events coming in the future.
Yeah. All right. Well, thank you so much for your introduction, and thank you all for coming. This is more like an informal talk, so I will just try to write down stuff there. Feel free to let me know if I am drawing like horrible things, if I'm not explaining myself. I will be more than happy to stop and explain everything slowly. I really like explaining things slowly, so I hope you're okay with that. And today I will talk about a technique that we use a lot in our group. We use the electrochemical double layer capacitance to measure the surface area. So this is a pretty simple technique, and I will explain some of the fundamentals, and then I will move on to some experimental examples. And what I find really interesting about this technique is that, it's not that popular. And it turns out that if you don't follow certain guidelines and if you're unable to do certain steps properly, you can get like overestimated values. You can overestimate your results. So I hope this talk is useful for you in case in the future you want to use this technique to measure the surface area of your materials. So don't worry, this is not like doing actual electrochemical. Well, we will do electrochemical measurements using this technique. You can do that. But you don't necessarily need to work with electrochemistry. Like, for instance, if you work with, I don't know, maybe nanoparticles, metal nanoparticles, and you don't want to test them for electrochemical performance, but you want to know the surface area, you can use this method, okay? All right, so I will just start very briefly. I think in the camera, yeah. I will just try to stick to these two points, okay? So first of all, I would like to start explaining the basics of some general concepts of the electrochemical cell. So are you guys all familiar with electrochemistry? Like, electrode, electrolyte, potential, current? Okay. But still, I will just briefly mention some concepts. So let's say that we have here an electrode, right? And we have here our electrolyte. So this is the electrode. Sorry, I'm horrible just writing here. And this is the electrode. All right. So turns out that the electrode, I would say that one of the best things about the electrochemistry is that we can control the energy of the electrons by using an electrode. Okay. So that means that if we apply a negative potential, we apply a potential difference. So in this other side, we have the positive electrode. If this, for instance, is the cathode, and this is the cathode, we have the anode on the other side. So the cool thing about electrochemistry is that we can apply a negative potential, right? So that means that we are raising up the energy of the electrons. So, or in other words, we're populating this electrode with a bunch of electrons here. Okay, so we have an overall, we have a negative charge. So let's say that in solution, we have a species A. So species A is a charged species, it's positive. So that means that if we look at the molecular orbitals, let's say that this is the LUMO of this species here, maybe we have only one electron there. So this molecular orbital is not completely occupied by electrons, right? So if we tune the energy, let's say that this bar shows the energy of the electrons in this spectrum. If we increase the energy here above this threshold here, more or less, basically what we can do is we can promote the electrons from jumping from the electrode to the species, right? Because basically this means that we have the electrode or the electrons in the electrode, they have a higher energy. And therefore this, reaction, because it's basically a reaction, we're moving electrons from here to here, it's thermodynamically favorable, okay? And this is called a Faradaic process or Faradaic reaction. Okay, so this basically means that we're exchanging electrons. One electron is crossing or it's jumping from the electrode, is crossing the electrolyte interface, okay? And in this case is reducing species A. So now species becomes just A, okay? However, what happens when we apply a energy or when the energy level is below this? Of course, this is not going to happen, right? Now the reaction is thermodynamically unfavorable. So that means that if we stay here, it's impossible to do this, right? We require more energy. So let's say that in solution, we have more species. And we have also so if this energy is not enough for driving this process, do you have any guess what's going to happen? What else could happen there in that system? Let's say that we have this energy here. So we have a few negative charges here. Any ideas? Migration of what? That's a great point. Right, that's correct. This is positive, right? So we have negative charges here. So this is basically electrostatic. So if the energy is not enough for, making the electrons jump from the electrode to the species, at least this energy is enough for, dragging these cations in solution close to these surface, okay? So these species are not reacting at all. They are just moving, and therefore they will give up on the surface here. And this is one example because there are several types of these processes, but this is an example of a, let me put it here, non-Faradaic process. So this is a non-Faradaic process, and basically it means that there's no exchange of electrons, right? There's no basically any electrochemical reaction happening. So there is only electrostatic interaction with the surface. Okay. Any questions so far? Awesome. Let me just remove this. All right. So another important thing here is that let's say that we plot the current and the potential. Something like this. So maybe you guys are familiar with linear strip voltammetry or some of these methods where we sweep the potential and then we record or register the current. So sometimes we see something like this. Okay. So very simple stuff here. I will go into a lot of details, but you can see that there's an increase of the current. Remember that the current is basically the amount of electrons that are being transferred. However, we see that at the beginning, let's say that here is 0. Let's say this value is like 0.1 microns or so. And here we have a way higher current, okay? So we can see that around this point here, we see an increase. And this increase is likely because of Faradaic process. So here it means that the electrons from the electrode are being exchanged with the species in solution. So here we say that this is Faradaic. And on the other side, we have non-Faradaic process. But you can see that still we have a current. So this current is related to this driving or movement or migration of a species towards the electron, okay? So we could say that, maybe I will put it here, non-Faradaic processes have something called charging current. Charging current and Faradaic processes we can call charge transfer current. We can see I and R. Okay. So in this talk, I will basically focus on this area here. Okay. Now, let me just, because I really want to use this scheme, because we'll use it more later. So the thing is that now, once we apply this negative potential here, we will have in solution. First, we have solvent molecules. So some of the solvent molecules will stay close to the electrode, right? Like water. But we also have positive charges here, right? So these positive charges are right next to the electrode, but in between you have solvent molecules. So this structure here is also known as the electrochemical double layer. And the electrochemical double layer is actually more complex than this, because you can also have absorption of the species. You can also have other interactions going on here. But today, just for sake of simplicity, let's just say that we have positive charges that build up on the surface, and we also have negative charges. So that's why it is an electrochemical double layer, okay? Turns out that this electrochemical double layer resembles a capacitor, right? I think you're familiar with the term capacitor. Basically, a capacitor is a device where we apply a potential difference, right? And therefore, charges will build up on two parallel plates, okay? And in between these parallel plates, we have a material that is known as dielectric or insulator. It's basically a non-conductive material. So therefore, these charges just build up there. So notice that this resembles this. We have negative charges, a dielectric, and also positive charges, right? So that means that we can use the same theory that applies for capacitors for electrochemical double layers, okay? And another interesting fact is that notice that only these positive charges will get close to the electrode surface. So let's say that here we coat the electrode with, I don't know, with a polymer, with epoxy, we coat it with Teflon, I don't know. This is a non-conductor material, right? So that means that charges will just build up here and not here, because here we don't have electrons, so there's nothing to charge here on this part of the surface. So that means that only the electrode surface is exposed to the electrolyte, and therefore only these charges will build up here, not here. And therefore, we can use these phenomenon to assess or to estimate the surface area, right? Because only the parts that are exposed to the ions will be related to this charging process, and that means the surface area. But we will explain more. I will explain more about that later. All right. Any questions so far? All right. Now, going back to capacitors. A capacitor is defined as, this is the main capacitor equation. So this C here is the capacitance. We have the charge and the potential. So basically the capacitance is the amount of charge that we can store at a certain potential. So if we apply a certain potential, we drive charges right next to the dielectric, right? And this is the capacitance. And the capacitance depends on the materials we use here, depends on the dielectric. Different types of dielectric have different dielectric constants. Depends on the different properties of the connection between these two. So therefore, this is a very, let's say that it is an intrinsic property that depends on the material we use. All right, so we have capacitance. Let's use CD here, because we'll modify it later. Because we can apply the same theory here for the electrochemical double layer. So therefore, in the electrochemical double layer, we can talk about something known as double layer capacitance. And the double layer capacitance is basically the amount of charge that we can store, or the amount of charge that builds up on the electrode surface. Okay. Now, I don't want to get into a lot of math because we don't have a lot of time. But if you know the Professor Bart's book, the first chapter explains like the math behind the things that I'm about to explain. Because basically it's dealing with differential equations and setting some conditions. But basically what I want to show now is how we relate this equation to the current. Because at the beginning I was explaining about current, charging current, and Faradaic current. In this case, this is related to charging current. All right. One more thing about this equation. Notice that if we solve Q, basically CD E, right? And therefore the current is proportional, sorry, the charge is proportional to the potential, right? And this is a constant that depends on the material. All right. So I was talking about these like equations in the Bart's book. So basically what I want to show now is that we have been talking about charge. How do we relate this to current? Well, we know that current in amps, for instance, the current is the amount of charge that, is crossing a wire or something per unit of time. Okay, so we can relate this equation by using this differential equation. The change of current, the change of charge per unit of time. If we change the charge, what's the other variable that we should change, or how can we relate this one to other variable in the system? Well, that's the potential, right? So another variable, we can say that this is the current. Another variable that changes, is the potential. Are you guys familiar with this? Have you seen this like term previously? Do you know what kind of variable is this one? The change in the potential with time? The scan rate. Scan rate, right? That's the standard. So that means that if we scan the potential in a certain way, we can also change the current because we're changing the charge, right? With time, so therefore we have the current. Does that make sense? All right, great. We move on to this side. All right, so I'll just get rid of everything and all right, let's go back to the math. So the thing is that this relation there, we have that the charge is proportional to the potential. So that means that if we use these differential expressions in that equations and we do some math and we solve the differential equation, we will end up with a equation that looks like this. The current equals the CDL, okay? And then we have the scan rate as we saw there because it's the change, right, of the potential with time. And these terms here, minus T. So this term here is composed by the time. So this exponential term is basically showing that there's some kind of decay or stabilization. And I will show you the plot in a little bit. We have the time. It depends on the time. It depends on the resistance of the solution, and also it includes other terms that could be, contributing to the resistance. And again, the double layer capacity. So if we plot this, we will see something like this. So I will show you two plots here. The first plot is the potential against the time. And the second plot is the current against time. So the scan rate works by switching the potential between, let's say, potential 1 and potential 2. All right. We're sweeping the potential from beginning to the end. So time 0, we start here, and we should see something like this. Okay, more or less. So this is time 2. Okay, this is the plot for potential against time, and this is the plot for current against time. So initially, we should see something like this. Something like this. This curvature here is because of this term. Notice that as time increases, this term here becomes smaller, right? Becomes 0, basically. And therefore, here at the beginning, we have this term causing this like increase, like exponential increase. And then we have this plateau. And this plateau happens because this term becomes 1. And therefore, here, this distance becomes scan rate double layer capacity. Right? Does that make sense? Great. So that means that if we apply a certain potential or a certain scan rate, we can find this current, and we can say that this current is a charging. Remember that here there's no electrochemical reaction happening. There's only charging current. So this current here, I see, is basically how much current I need to charge the electrode surface at this scan rate or at this potential, okay? And we can use this to know, later I will show you the surface area, okay? Any questions so far? Yep.
How did you write the equation on top? IC.
Oh, IC equals double layer capacitance times the scan rate and times this term. So this term is 1 minus E to the minus T time, right? Resistance R, RS, and double layer capacitance. This is divided by this term. Right?
I guess my question was how did you arrive at?
Oh, so how do I get to that one? Yeah, you need to solve this differential equation. Yeah, you need to take into account all the potential contributions. The potential is caused by the potential that you apply, the potential like the ohmic drop due to the resistance. So you need to take all that into account into this equation, and then you need to input these differential terms here and solve for I. Okay. But yeah, you can find the entire procedure in bar speed. Yeah, and it's the first chapter. The first chapter is the easiest one. You don't get a headache when you read that one. The rest of it is really hard, but it's nice. All right, so
is there no temperature for current? I mean, there's no temperature in the equation, is it? Like I don't know nothing about that. So just asking.
Just asking what? Could you please repeat?
Is there no temperature term in IC?
Oh, temperature term here.
Yeah, temperature dependence.
We're not considering any like temperature dependence here in the equation, but some terms here may depend on the temperature, like for instance, the resistance.
Okay.
Yeah, like some terms may depend on the temperature, but we're not including any kind of like Arrhenius equation. Yeah, but this looks like an Arrhenius equation, right? Because it's exponential. All right. So now the thing is, I show you this behavior where we use the current. You see how much time that you have. So let's say that this is one scenario where we just see the potential in this way. So notice that here, yeah.
Sorry, one quick question.
Yep.
So in the earlier plot that you made, there was a point where the current was constant and then it shoots up.
Yeah.
So my question is, will there always be a current flowing? Because like you said, you have to charge the electrode to a certain level before the current starts.
Yeah.
Right. So is there a scan rate? Can it be so slow or start so low that initially the current is zero and then it increases? Like,
that's a good point. If you change the scan rate, and it's actually what I'm gonna show next, you will change that charging curve, but it's never like really close to zero, right? Because even if you have a very small scanner, like 5 millivolts per second, this current will be really small. But you need to have like this current, because the first step is always charging the electrode, is dragging particles close to the electrode.
Okay.
So you will maybe see a very tiny current there, but this is because of charge.
so that's not the charge transfer current, that's the current that's being used to charge the electrode.
Yeah, exactly.
Got it.
Right.
Can
Yeah.
you also explain the scan rate, like what exactly is a scan rate?
Oh, sure, absolutely. So the scan rate is basically in this plot, the slope. So the scan rate is telling you how fast or how steep, right, you're scanning the potential. You're changing the potential between 1 and 2, how fast. Like for instance, if you do something like this is T2, right? It's taking, well, imagine this one goes up and up and up until this point here. It's basically meaning that you're spending more time just to reach the same potential difference, right? So this is slower, okay? All right. Next condition or next scenario, let's say that we have the same plots. Now we have I and I. So if we apply a potential scan that goes from 1 to 2 and then going back, right? We should see something like this. Change the plot. This is time 0, current 0 in time. Okay, we should see something like this, increase, then drops, and then we have the same behavior here. Why? Just because here at the beginning, we're sweeping in the positive direction, right? And then we're sweeping the potential in the negative direction, okay? So here, in other words, we're building up positive charges and the negative charges. But notice the reason why I'm showing you this is that notice that this magnitude here, the magnitude is the same. So this is a scan rate, CDL. This is minus scan rate, CDL. Okay, this magnitude is the same. So it doesn't matter if we sweep back and forth, we should get a symmetrical response. And this is important because one of the rules to know if this measurement is working fine, like it's trustable, is if these shapes are symmetrical. Okay, because this magnitude should be the same. It's just a matter of positive sign and negative sign. All right. So now going back to what you guys were asking about the charging current and why it changes with the scan rate. The scan rate is basically how fast we're changing the potential, right? So if we apply a potential really fast, let's say that we have different scan rates, like 100 millivolts per second and 1000 millivolts or 1 volt per second. So that means that on the same dimension of time, in the same time, like 1 second, in one scenario, we're charging 100 millivolts, and in the other one, we're charging 1000. So that means that in one scenario, we're dragging more charges, right? Because it is a higher potential that we are applying on the same time. Okay, does that make sense? All right, great. So that means that if we have a plot of, let me just change it. The plot that I showed you previously, the plot of current, and then actually, let me see if it's not that confusing, but another way to plot is instead of using time, notice that these two charts share the same axis. So we can plot the current against the potential. So a more like common way to plot this is to show something like this. So here we have the potential and the current. Okay, so this is the way we plot like these behavior. Just instead of using time, we use the potential because we know the scan. So this is the shape we get for, let's say, a scan rate 50 millivolts per second. Okay, so it turns out that if we change the scan rate, like if we scan the potential maybe at 10 millivolts per second, we will see something like this. Okay, so this means that this current is proportional to the scan rate. And actually it turns out that it's true, right? Because in this equation, we can see that the charging current, like this current here, right, is proportional to the scan rate. So if we increase the scan rate, we should see a higher charging current, all right? And therefore, we can use this relationship to get the double layer capacitance. How? Move on to this part again. Basically, if we plot the charging current, right, with the scan rate, we should see a linear behavior, right? Because if we increase the scan rate, we should see this magnitude getting larger and larger, and it's proportional to the scan rate we apply. All right. And if we use this plot, the slope equals the double layer capacitance. Right? Does that make sense? This is the general theory about this technique. And just a final remark on that before I give you some experimental evidence is maybe you're wondering, having just talking about double layer capacitance, where's the area? We need to use the area, right? And you don't see here any like square centimeters units. Well, this is, remember that this is for measuring the double layer capacitance of an electrode surface. So let's say again that we have an electrode. So if we know the area beforehand, let's say that we use a powerful technique like maybe BET or maybe AFM, atomic force microscopy. With AFM, we can basically map the surface and we can know precisely the surface area. So let's say that we have a very beautiful electrode. We have a shiny, smooth, and perfect, I don't know, platinum, nickel, whatever material you want that is conductive. And we know by using AFM, BET, any other technique, that the surface area here is 1 square centimeter. Okay, if we know that, and then if we measure the double layer capacitance of this material, now we can relate the double layer by the surface area, right? And this is known as the specific capacitance. So this specific capacitance is only applicable to this material, right? And this material as pure as we use it. The reason why this is helpful is that imagine this is, I don't know, this is nickel, just nickel foil, pristine nickel foil. But let's say that later you synthesize a rough material that is, well, this rough is not smooth, so maybe now it's something like that. Okay, we know that here all the charges built up perfectly flat on a smooth surface, right? If we move on, but we're using the same material, we're using nickel. Now the charges will have more charges like this, right? But we're not changing the material. So that means that if we use this specific capacitance, we can get the surface area. In other words, We know the capacitance here, 1. Here we know the other capacitance 2. So if we know here the surface area, we can get the surface area from here. Does that make sense? Great. So that's the way the technique works. And now I will show you some experimental evidence. Just before doing that, I will explain really quick some important considerations that you need to take into account. The first one, the material must be conductive. If your material is not conductive, you're not able to, apply negative bias and drag the charges. So the material needs to be conductive. Only metals, some metal oxides are conductive. Semiconductors, it depends if you're sure that the material is conductor when you apply a certain potential, or if you shine light, those kind of properties. But you need to make sure the material is conductive. If it's not, this measurement is not reliable. Second condition, remember this process can only be measured under non-Faradaic conditions. So let's say that you have an LSB or CV that looks like this. So if you have, let's say something like this, like platinum or something, you're able to do this measurement only in this portion of the curve, right? Because here you have reactions, here you have reactions. So these reactions will interfere because here you have both charging and Faradaic current. But here you only have charging current. So for instance, one initial step is find the best potential window, okay? Second thing, well, this is the second. Third thing, let me see if I can use this. Do you remember that the behavior of the curve is something like this? Like flat. Remember that this distance here was the magnitude of scan rate times Doppler capacitance. Well, you need to make sure this plateau forms, because if you see something like this, well, where's the plateau? So you cannot say, oh yeah, this is the part where this term becomes 0. Okay, so you need to make sure this term becomes 0. And experimentally, it is just by looking at the shape of this potential window or these potentials. So for instance, if you do your analysis just here, you're unable to see this plateau. So you need to extend the potential window. So for instance, in this scenario here, instead of just running it here, right, you should increase the potential window like this. So you are able to get this plateau, and you are able to get this term there. Okay, so this is the third consideration. Fourth consideration, we're changing the scan rate. And because this is a capacitor and non-ideal capacitor, we should be able to replicate this process at any scan rate. So you should try scanning different values, like for instance, or what I'm trying to say is, if you have this plot here, current and scan rate, right? The more points you have, the better. Because you can say, okay, this material behaves like a capacitor from 10 millivolts per second up to 1 volt per second. Okay, if this is true, that means that your material truly behaves as a capacitor here on this section of the curve. Sometimes you will see that this behavior only happens like a very small scan rate. And sometimes some people argue that's not reliable. Because when you have a very small scan rate, you will have, as you mentioned, you will have like a very tiny current, like nanoamps or like 5 microamps. And some people may say, oh yeah, but it's flat. But yeah, you're just scanning 10 millivolts per second. So it's like really, really small. So you're unable, sometimes you will have noise. So you will see something like this. So it will be, you won't be able to see this plateau clearly. So if you increase the scan rate up to 1 volt per second, you should be able to see a clear plateau. If you don't see it, either the potential window is not in the right position, either the material maybe is not conductive, so that's why you're unable to see this shape. Okay. Last condition that I want to emphasize today is the one more thing. Sorry, this is the equation for maybe you can remove this one here. Maybe this equation is familiar to you. This one resembles this equation, right? The slope. But turns out the double layer, the electrochemical double layer is not an ideal capacitor because we have solvent, we have all other interactions. So instead of using this equation, it's better to use an equation that resembles a power law, something like this, right? Instead of this. Why? Because this exponent here, if it's 1, if it equals 1, it's just basically this equation. But if it's not 1 or lower, smaller than 1, that means that we're deviating from the ideal behavior of the capacitor, right? So we want this value to be as close as possible to 1. So if you use this fitting instead of this one, you can get an idea of how ideal your capacitor is. Okay. And if this value is like, let's say 0.8, maybe that means that the capacitor is like deviating a lot, and therefore maybe it's not truly conductive, or maybe you're not using the right potential width. Okay. So just to show you some final insights, let me share the screen with people in Zoom. Okay, I hope you guys can see the screen. I think I need to wait. Well, what I'm showing there is come on. Okay, what I'm showing here is this is a really cool paper about explaining double layer capacitance measurement. So last consideration, water is not an ideal solvent. Why? Because with water, as you can see here in this part here, with water, you have, for instance, proton intercalation. Also, when you work with water, you may have some corrosion problems. Like if you immerse a metal in solution, maybe the material is gonna start corroding. So turns out that working with organic electrolytes like product solvents, like for instance, potassium hexafluorophosphate in acetonitrile, works better, because if you do that, you can prevent any kind of interactions or ion transfer reactions that are not desirable. Okay, and this is the way the shape of these CV scans should look like. Okay, so in this paper, it is a very interesting paper because they compare the specific capacitance of different materials here, as you can see here, and notice how the specific capacitance deviates a lot. So what they did here is they measured the surface area using atomic force microscopy. They found the area, and then they measured the double layer capacitance. And notice that in water, in aqueous electrolyte, you have a lot of deviations. Like sometimes you have very small specific capacitance and then some large capacitance. And the reason why this is like wrong is because some people, like for instance, if you use, I don't know, maybe palladium. With palladium, the value is around 10. So you can just use that value and that's it. But some people, when they synthesize specific materials, they assume that the value is around this average here. Okay. So they say like, okay, I am not synthesizing nickel sulfide. I synthesize nickel phosphide. But I think the average is like around 30 or 25. So I can use that value instead. And as I told you, if you know this value, and if you know your double layer capacity, you can get the superset. But that's wrong, because notice that this average is like this average value is not close to, for instance, values from, was that iron, right? So it's deviating a lot. So that's wrong. But what happens when you use organic electrolyte? When you use organic electrolyte, you can prevent these side reactions from, deviating your estimation of the double layer capacitance. And when you use organic electrolyte, now notice that this average is like 11. So this value of 11, the specific capacitance of 11 microfarads, by the way, farads are the unit of the capacitance. This value is closer to all these materials here. So now you can use this average value instead of using like 30 or 25, only if you use a product electrolyte. And just to finish this, I will show you some photos. So this is like the typical setup we use in the lab. My undergrads are here. They are very happy to work with that. I'm pretty sure they are. And you can see that basically it's a simple 3-electrode cell. We have a reference electrode, counter electrode, and working electrode. These are some examples. So this is just bare nickel foil. Notice that we have these like almost like a rectangular shape. So this is what we expect to see, especially here it's a metal. So we should not expect any problems here. Notice that we're scanning from 10 millivolts per second and we are going up to 1 volt per second. Okay. Then this is the fitting. Notice that we're using this power low fitting. So notice that the alpha value, the one here, it's 0.95 more or less. So it's closer to 1. We'll see another example later. But yeah, we try to get a value that is as close as 1, as possible as 1 to 1. Okay. And from the slope, from the B term, we can get the double layer capacitance, right? So if we know this value here, 7.2 microfarads, and if we divide it by the specific capacitance, the 11 that I showed you in the previous slide, we can get the surface area. Okay. Notice that it doesn't matter if we use the positive or negative values, and it's like the values anodic currents or cathodic. We should get more or less the same value. Okay. This is stainless steel. We see the same behavior. We see a almost perfect rectangle. Also, we can use the same scan rate range. And again, we should see a value that is like 0.9, which is expected. And notice that we can also get the double layer capacitance. This is a stainless steel mesh. So for instance, if you have a counter electrode and you want to know the real surface area of your counter electrode, like platinum, stainless steel, or other material, you can do that. Now, this is an example that I remember when I did the first time I did this, I was like really happy. And then one of my friends in the Mullins group was telling me, oh, this is wrong. And I was like, why? I really like that shape. It looks like a rectangle. I can see the plateau. But turns out that, as I explained, one common issue is that if the material is not conductive, you may have some overestimations. Because notice here the units, milliamps. So this is really high. And if we look for the double layer capacitance, we get a really high value. And this large value is just because, and also noting the exponent here is 0.8, so it's getting lower, smaller. And this is because nickel hydroxide is not a good conductor compared to metals, of course. So for instance, if you have nickel 2+, compounds like nickel hydroxide are not as good as metals. And therefore the conductivity is not good. So that explains why the shape looks different to the others, right? It's completely different. And also another thing, do you see another difference from this data set? I told you one difference is the current. What else?
Smaller scan rate.
Smaller scan rates, right? We were able only to get these behavior from 5 to 50. We tried, my undergrads know this, we tried like faster scan rates and the result was worse. So that means that probably the material is not conductive. So at first I was like, okay, I will just pick these values. And then my friend was like, oh, the reason why you're having trouble is because it's not conductive. So actually, I'm not showing these results today because we did these experiments last week, actually. But what the way we were able to solve this issue was oxidizing the material. Because when you oxidize nickel 2 plus into nickel 3 plus, nickel oxyhydroxide is conductive, is a better conductor than nickel hydroxide. So we were able to get really nice data. But unfortunately, I didn't have enough time to plot all the details, all the results for today. But yeah, that's the main way we can use this technique. Sorry if I was explaining a little bit fast and also almost about time. But if you have more questions, let me know. I work in the Mullins group. Or you can also find these papers. As I told you, these papers are really good. So I strongly recommend taking a look at this paper. It's from a very famous professor in MIT, Dr. Yogi Surendranath. And he has a lot of work on electrochemistry. So if you're interested, take a look at it. And that's it from today. Thank you so much for your attention. Any questions? I know that it's almost 6, but if you have any questions or something, we can talk. Yeah.
So is this the only technique that can measure electrical layer capacitors, or are there other techniques that are used?
That's a great question. There's another way to measure double layer capacitance, and that's electrochemical impedance spectroscopy. With EIS, you can also measure the double layer capacitance. And actually, in a really good paper that I couldn't explain all the details here today, but in this other paper, they compare the double layer capacitance from EIS and this method, and they should be pretty similar. But yeah, you can use EIS as well, right?
Yeah, I was more interested to know that because we are trying to model EIS, etc.
Yeah.
So yeah, one of the questions we try to answer is how to get meaningful data out of the EIS spectrum.
Yeah. You know, the reason why sometimes some people use this method instead of EIS, first is because EIS could be more problematic because of the fitting. So some people have like the tools to do fitting, but other people, they don't have like software or they don't know programming tools. So this method is really simple, just using CV, just plotting straight line, and that's it. Really straightforward. However, if you can complement both techniques, if you use EIS and this one, and actually sometimes reviewers ask to do that, you can get better results. But yeah, definitely you can use EIS. But the challenge is how to simulate and fit EIS spectrum. That's the challenge. Yeah. Any other question?
So I noticed when you were talking about the overall response that you get out of different stand rates, you end up getting more current out of a higher stand rate.
Yeah.
As a magnitude.
Yeah.
And I was wondering if you could shed some light on the physical consequence of that and what that means. Just because if you think about arriving at a voltage, if you just consider it conceptually quickly, you would say the same voltage will get the same amount of charge.
Yeah.
Overall. So I was curious what that meant physically, that you have more charge in case of the other.
That's a great question. So basically, or physically, what it means is that you are decreasing the diffusion layer. Because when you have a faster scan rate, you apply like a high potential really fast, and therefore you're dragging more ions close to the surface. So the current is at the same time is large, because these diffusion like layer or space where these ions move, they move really, really fast. So because they move really fast, you're dragging a lot of ions, and therefore you end up with a lot of current.
Thank you.
Yep. All right, guys. I think some people on Zoom may have some questions. Sorry about that. I see a couple of comments. Let me see. Okay. So in the chat, they're asking, is the double layer capacitance an approximate value or precisely as accurate as BET? It depends. The disadvantage of BET is that you're measuring the surface area by absorbing gases. So gases can absorb on almost any surface. So, BET is a technique, Bromer, Emmett, what's the T stands for? No, it's Taylor. I think it's Brown Emmett Taylor. I think someone in the chat is helping us. Oh yeah, maybe not. Well, the thing is, it is a technique that is used to measure the surface area by absorbing gases. So the downside of using BET is that if you have some portions of your material that are not conductive, you will get an overestimated surface area, because basically you're saying, oh, more surface is there, but in fact, only the electrochemically active surface area can be utilized in the electrochemical reaction, right? So they will be different. Taylor, yeah, thank you, Shika. Yeah, Bromet Emmer Taylor. Okay, what are there materials for which CDL isn't useful in estimating the surface area? Sure. As I explained, when you have like double layer capacitance in materials that are semiconductors, it's tricky, because some people will argue your material is not conductor, so you will have definitely you will have trouble estimating the surface area. I will say that in my experience, that's the only example that I know about that. It's just if the material behaves as a capacitor, the double layer capacitance works, but if not, you cannot use it. It's not reliable. Another question: can a square wave voltammetry be used to measure CDL? As long as you are able to get a defined plateau where you can relate the charging current, or in other words, if you can get the charging current at different scan rates, you can use it. I have not used a square wave voltammetry, so I'm not familiar with the kind of shapes you get. I have seen some shapes in other papers, but I have not seen any like paper using it to get the double layer capacitance. So unfortunately, I don't know a lot about that technique, but as soon as you can get the charging current, you should be able to relate the current to this equation here. Charging current equals double layer capacitance and the scan rate. What's the A from BXA? Oh yeah, this A here is an exponent. It's just a term that is telling you this value is close to 1 or is close to 0. And as I explained, if this one is 1, this one becomes this equation. Okay. The particular reason for question 3 is that square wave voltammetry, it minimizes capacitive current. Oh, okay, I didn't know that. I think it's interesting to look into more details into that, because yeah, I think a square wave voltammetry works a little bit different. So yeah, I'm not sure what's the way how it minimizes the capacitive current. Sorry about that. All right, so I think those are all the questions from here. So thanks again. I'm not sure if there's no food left, right? Or oh yeah, sure.
How would you recommend finding potential window that you're taking measurements in? And like, let's say you have a potential window, supposedly there's no Faradaic processes, but it's like, is very large. Do you recommend taking that whole potential window, or like saying to 100 mil, 200 mil?
That's a great question. So about the first question, there are 2 ways. One way could be just doing a wide scanner, a wide scanning the potential in a wide region. So you can see like the plot that I show where you have different things. However, if you do that, you may oxidize or reduce whatever you have in your sample, so you may change the composition. So an easier way to do it is just to measure the open circuit potential. So the open circuit potential is basically the potential where no reaction happens. It's like the equilibrium potential. And the way you measure it is just basically, actually you can use a multimeter. You don't need a potentiostat, you don't need anything like that. You can just put each terminal to each electrode, and the potential that results there is the equilibrium potential of the system, because there's no current going across the system. So that potential, if you wait enough time until your system reaches the equilibrium, that value should be located around the non-Faradaic region, because there's no spontaneous reaction. Notice that it only applies for non-spontaneous processes. So for batteries, that doesn't apply for batteries, right? Unless you test the material outside the conditions where you do it. like if you grab the lithium cobalt oxide and then you put it in another system with another counterweight. So using the open circuit potential is a way to find the equilibrium potential, and around that equilibrium is where no reaction happens. So you can use that. About the second question, so the wider the potential window, the better, because as I explained, you want to see like this plateau until it develops completely. But you know, at the same time, there are some like practical limitations. You don't want to spend like several hours just measuring the whole thing. So maybe you can limit to maybe 100, 200 millivolts. Like for instance, some plots that I showed there, the potential window is like 400, because I just wanted to see this plateau completely, but it depends. I would suggest to maybe stick to 100 or 200 millivolts at least, because if you use less than that, you won't be able to see the plateau. Okay?
Another question is,
Uh-huh.
in terms of like the resolution of the scans, like how many points per scan?
That's another great question. Actually, in another paper that I couldn't explain today because of time, they also recommend optimizing something called the step size, which is what you asked for. This step size is basically how many points you register for each scan. Of course, it would be great to, you know, record as many data points as possible, but again, that's more related to practical limitations. Because if you have like a very long or wide window and you're recording like different scan rates, maybe you will have storage limitations. I don't think it's quite common. So sometimes you can say, for instance, let's get a point every 0.1 millivolts. So that means that you will have a bunch of points, like so many points. Sometimes you can optimize it to maybe use like 1 every 1 millivolt you will get a point. And also I will say that the best thing to do is just to optimize. Just try different values. Maybe if you use like 5 millivolts, you won't be able, maybe you will get like a lot of noise. But if you decrease that to maybe 0.1, you will get a more steady response. So I think the best thing to do is always to optimize your conditions first, and then you can get the double layer capacitance with the best conditions.
If you use different organic solvents, will your capacitance change?
That's a great question. So the thing about organic solvents is that organic solvents are also, they may have different conductivities. So yeah, the conductivity, the double layer capacitance depends a lot on the solvent that you use as well, right? So you should be careful with what kind of solvents you use, not because the double layer capacitance may change. Like in the equation here, notice that instead of looking at the double layer capacitance and it's gonna change because of the solvent, the term that is gonna affect the most is the resistance. Okay, so the resistance is the main reason why you should stick to one solvent. I would say that the best thing to do is to repeat the experiment with the same solvent. Right. And again, for instance, if you change with water, you will have different contributions. If you have, for instance, other organic solvent instead of acetonitrile, you will have lower conductivities, and therefore you will have maybe overestimation or underestimation of double layer capacitance, because now the material is the electrolyte is not conductive enough to make sure that the charges get to the surface. So that's another limitation.